select record, I'm going to zoom. So now we're off and running. Okay, so today's the 20th. And we have a couple of new things to learn. I'm going to do these in a reverse order. The first one is powers of I. And there are occasions in mathematics where it's good to know what various higher powers of I are equal to. So we're going to start, we're going to find a pattern, like a table of this. And by the way, the objective here, do you remember this? Have you seen this before? Good. So this, I did. This is marvelous. So we're going to go real quick. So remember that we want to know what any power of I is. Where we're headed here is I want to be able to tell you, I don't know if it would ever happen, but I want to be able to say, hey, Christian, what is I to the 2,351st power? And I want him to be able to simplify it down. And if you've seen this before, you recall that it has to be one of four answers. All right. So what happens is powers of I are trapped, and they're trapped in a modular arithmetic cycle. It repeats every four. You get four answers and then you repeat, and then you get the same four answers and then you repeat. So to make the cycle visible to you guys, we need to start by talking about I to the power of one. And I to the power of one is, of course, just I, right? You guys all remember what I to the power of two is. You know this one from yesterday. You should. It's negative one. Good. What is I to the power of three? Well, that one you may have forgotten over the summer. It's negative I. Good. And I will explain that for the people who maybe it's been a while. For you guys who I had a couple years ago, did we let me let
did. I just don't remember.
okay, let me give you a quick side note as to where that comes from, because I just, in fairness to you, I want you to have a little snippet of how did that happen? So here's the deal. I to the third, I'm going to switch colors here for a second. I to the third can be written as I to the second times I to the first. I hope you agree, because the two and the one can be combined to make three, right? And why I would do it this way is because I have prior knowledge that allows me to fill those in. Like we already know that I to the power of two is negative one, right? And we know that I to the first power is I. Then we can put those together, and that's why I to the third power equals negative I. Do you see it? So I just want you to think it's like black magic. We're not just making stuff up here. And the same can be done with I to the fourth power. And I to the fourth power, do you guys remember what it equals? It equals one. And why it happens that way is because, and I'm going to switch colors again, is because if I wanted to break down I to the fourth power, there's nothing stopping me from calling it I squared times I squared, because two and two make four. And what is I squared? Negative one. And what is I squared? And what is negative one times negative one? One. It's at this point that the cycle repeats. And what happens at this point is if I were to jump ahead, I'm going to. So when I jump ahead to I to the fifth power, I realize now that I can now take every problem from here on out and essentially just disrespect it by pulling a huge chunk, a redundant, pointless chunk of itself out. I can take I to the fifth power and say, you know what? I'm just going to call you I to the fourth times I to the first. And why that's hilariously useful is because what's I to the fourth? One. You just laughed at the problem and just slapped it around a little bit. So if I to the fourth is one, it becomes an identity and says, well, you can just essentially remove me without consideration. And one times I is, you guessed it, I. And it's at this point that the cycle repeats for that exact logical reason that, like I to the sixth power, the explanation goes the same way. I say, well, if you want me to show you what I to the sixth looks like, well, here it goes. It's I to the fourth times I to the second. And what happens every time we pull out an I to the fourth? It just goes away. It's one. It's pointless. It's going to keep happening. When we get to the next iteration of this cycle, we can start taking out I to the eighths, because I to the eighth is going to be one. Or you could take out I to the 12th, I to the 16th. Anytime you take out some I to some multiple of four, you are essentially just pulling out a portion that's redundant and pointless. That's why the cycle repeats. And so I to the sixth is really just I squared, which is -1. 1 second there, Zachary. And I to the seventh is -I, and I to the eighth is 1, and the cycle just repeats, repeats, repeats. So yeah, Zach.
I think you're probably gonna get to it, but didn't we figure out like you divide big numbers?
You do. Yep, I'm headed right there. So that was actually, it's almost like I paid you to segue me like that.
Please excuse the interruption. We need the following students for the office, please. Jordan Boljak, Callie Klein, Joshua Keo, Alexis Snyder, Callie Garcia, Dane Wiltusen, Tatum Rear, and Jack Thomas.
So remember that the fact that by the way, this is good for your upper level math. There's a class you might wind up taking. I took it at UW and I don't like it. It was called abstract algebra. Hardest class I ever took, where you start to study something called modular arithmetic. And the idea of modular arithmetic is that repetition occurs within number sets. So like this is like we're doing mod 4 in this problem because we're taking a pattern that is 4 long and then we throw it out, start over, throw it out, start over. So when you recognize that a pattern has a length of 4, then what you can start to say is, wait a second. So can I take bigger powers of 4 and divide by 4 and only worry about the remainder? Yes, that's the whole idea. So when I ask you for I to the 2,351st power, all you have to do is take 2,351 and divide it by the length of the pattern, which is 4.
And then isn't it? If your decimal is 0.25, it's 1.
Right. So let's do. Yep. And let's do it manually at first. And then we will, of course, go to calculators to look at decimals. But I want you to see the actual R equals like 1, 2, 3 things. So if I divide this out, we're going to go all like 5th grade mode on this thing. 4 goes into 23 5 times. 4 times 5 is 20. 23 minus 20 is 3. Drop the 5. 4 goes into 35 8 times. 4 times 8 is 32. Subtract, you get 3. Drop the 1. You learned this years ago. 4 goes into 31 7 times. 4 times 7 is 28. And all this stuff prior to this point is just work. What's the treasure at the end is the number that I'm going to write in yellow, and it's this. What is that called? It's called the remainder. And that's how modular arithmetic works, is if you can give me the remainder, you're essentially throwing out all the redundant stacks of repetitive garbage. So if the remainder is 3, we now have enough information to say where in the cycle should we go. And bottom line is this. The answer is either going to be I, -1, -I, or 1. Does anyone remember the pattern of what goes where? If the remainder is 1, what is the answer?
No, 1.
Say again. The answer is I. Correct. If the remainder is 2, what is the answer? -1. If the remainder is 3, what is the answer? Now, I asked this question, be careful, choose your answer wisely. What is the next remainder that I should write?
0.
Thank you for not saying 4. Good. Remember, if you divide by 4 and get a remainder of 4, you need to check your skills, right? That doesn't work that way. So there are 4 possible remainders when dividing by 4, and they are 1, 2, 3, and no remainder. And if you want validation of this, just check it for yourself. Like these are the 4 possible answers, and it's easy. It's almost impossible to miss these now. If you have this purple table, if this purple box is in your notes, you just almost can't go wrong. Now, the question becomes, what does that look like when I use a calculator? Well, a remainder is out of 4 in this case, since the cycle is 4 long. So like on this problem down in the corner, way down in the lower right corner down here, if I got a remainder of 3, that's 3 out of 4, which means that the remainder is actually 0.75. And I'm showing you this as a courtesy because you're probably going to do most of these problems by typing in the exponent divided by 4 and then just looking at the remainder in its decimal form. I would say the vast majority of us aren't going to sit around and do long division by hand. Having said that, when I get a remainder of 2, what is 2 over 4? 0.5. So when you get a decimal that is 0 point something 0.5, then you know the answer is -1. And what is the decimal equivalent of a remainder of 1? What's 1 out of 4? 0.25. So I can't make it much more user friendly than this. What everything up there in that purple and white area, that's your shopping zone there, okay? So let's just take it for a quick spin and then we'll head on to the other thing we're doing today. So going back to that, by the way, yeah, the answer to that one was what did we get? A remainder of 3. So the answer was -I. All right, let's practice. Let's work together and find I to the power of 422. So you grab that electronic calculating device or not and divide by 4. And you're not interested in all the stuff that comes before the decimal. It's going to say 105 point something, and you're like, blah, blah, blah. I'm not interested because the 105 is all the packets of redundant stuff we want to throw away. We're trying to scrape all that off the surface. What's the decimal? 0.5. So what's the answer? The answer is -1. Got it? Let's try I to the power of 36,428. So if you multiplied I by itself 36,428 times, what would the answer be?
0. So it's a 1.
1. If the remainder is 0, the answer is 1. So like if we were studying this in the context of the table that I just scrolled down away from, this would be one where it would be essentially like at the bottom of a column. Like, right? So do you have any questions about that? By the way, I forgot to say this last year. I think I caught it later on. This you'll also see this with multiplication. So you might see like I to the 5th times I to the 9th times I to the 21st. So going all the way back to the day when we learned about exponent rules, for some of us it was 8th grade, some of us 7th grade. Who knows? How do you put those together? What do you do with the exponents? You add them together, right? And so it really just winds up combining into one expression that says I to the power of 35. And then from there, what's the remainder when you divide 35 by 4? How many times does 4 go into 35? 8, with a remainder of 3. And a remainder of 3 puts us at the 3rd spot down in the table, which is negative I. 3rd spot down is -I, right? 2nd spot down is the -1. Do you have any questions about powers of I? All right. The second part of the notes for today is going to be the harder part. So that was, I think, kind of a walk in the park. This one's a little bit rougher. So this one is division. So dividing complex numbers. I hope you walked away from yesterday's lesson and thought to yourself, adding complex numbers is easy. Subtracting complex numbers is easy. I just have to remember to not botch the double negative thing at the end. Multiplying complex numbers is pretty easy. I got to watch out for those I squareds that switch to -1s. You'll walk away from division and think, that is definitely the hardest of the 4. But it's not very difficult overall. You ready, Zane? Do you need a moment? Do you need a minute break or 30 seconds? Or are you going to be okay? You sure? All right. Here's the deal. When it comes to dividing complex numbers, your mission is to make the bottom not be a complex number. That's it. In a nutshell, this is going to feel less like we're actually accomplishing a division problem. It's going to feel more like we're just fixing the bottom, because that really, at the end of the day, is what we're going to do. So you would agree that the number I'm circling in yellow is called an imaginary number. I hope after yesterday that you agree. That's not a real number, is it? Because it's got that 4i, negative 4i at the back of it. So our mission is to say, and if you're really paying attention yesterday, you're going to know the answer to this question. How can I turn an imaginary number into a real number? How do I fix it?
We
Say
do
it.
The conjugates, right?
Bless your heart. We're going to multiply by the conjugate because I learned yesterday, hold on, shut the front door. If I multiply by 2 plus 4i, something cool happens, right? You remember that when we multiply complex conjugates, it's not like other problems, how the middle term cancels out. But if I multiply on the bottom of this fraction by 2 minus 4i, I also have to multiply on the top of this fraction by 2 plus 4i. And this is what your problem should currently look like. Can anyone very quickly flex on all of us and tell me what the answer is to the bottom multiplication problem? Ready, set, go. Yeah.
Yeah.
20. And remember, in case you're a little lost, that's 2 times 2 plus 4 times 4, right? Conjugates are sweet. You don't even have to like show work. You just go multiply, multiply, add. So we did it. We fixed the bottom. Unfortunately, there's some collateral sort of damage now that we have to deal with. And that is that, hey, again, if you do it to the bottom, you got to do it to the top. And the top is a thing. It's a thing. It's its own dang multiplication problem. So I'm going to go as slow as I can. Here we go. What is the answer to the first multiplication on the top? It is 10. What is the answer to the far outer edge multiplication problem on the top? Plus 20i. What is the answer to the middle multiplication problem? 6i. And let's see how quick you want to go. We should be at a point, at least by the end of the day today, where we don't write down what I'm about to write down. I'm going to write down the we were just learning it thing. If I multiply the back by the back, yeah, I get it. I get plus 12i squared. But remember, that's sort of a rookie move because what do we know I squared is going to become? -1. The net result of which is really that the plus 12i squared just becomes -12. So rather than writing plus 12i squared, I could just save a minute and just write -12. Still with me? Got 2 steps left to do. The next step is to just combine and simplify the top and make it look pretty. So when I make the top a nice proper complex number, I'm going to put the 10 and the -12 together to get -2. And then I'm going to put the imaginary terms together to get plus 26i. And then I'm going to put it all over 20. And that feels like it really ought to be the end of the problem, but it's not. It is not written right now as a complex number. It's written as a complex number divided by a real number. And so what we're going to do is we're going to do some DDD, double diagonal division. We're going to break it up into 2 pieces. The first one is from right here, and it is -1/10. That is now our A value. That's our real part. The second one is going to come from the green right here, and that's going to be plus 13/10i. And what's beautiful about that is now that is in perfect standard complex form, a plus bi. -10 is our real part, 13/10 is our imaginary coefficient. It's perfect, it's gorgeous, and it's done. So the moral of the story is we multiply the top and the bottom by the conjugate of the bottom, and then we simplify the top and then do the DDD, the double diagonal division, and call it a day. Let's practice that skill one more time at least, and then I'll get out of your way here. We can do 2 more if you'd rather. I don't really care. Scale of 1 to 10. 1, I have no idea what you just did. 10 is that was easy. I got it. Where are you? 5, 8. No, is that a 9? Is that a 9? 8? 9?
8.
What is that? 5? Yeah, let's do another one. Where are you at? 8. Corbier? Listen, if we can avoid the large numbers, because again, you're just making your own problem here. Could someone please write
Please
me?
excuse the interruption. We need the following students to the office, please. Tegan Savage, Leah Yearout, Caden Painter, Diana Baltazarez, Casey Croughton, Addison Jeffrey, Callie Klein, Jax Hink, Owen Soul, and Grady Baker.
I thought we were finally all going to figure out that Shelley is actually a robot and that she just malfunctioned and went into the spin cycle. Caden Painter, Caden Painter, Caden Painter, and then you can hear like Mr. Townsend in the background, like, God, shut her off, like. Someone write me a complex number.
7 minus 3.
Thank you for a nice normal complex number. Can I have another one?
9 minutes.
9 minus I. I'll take it. What a gorgeous problem. So I take zero responsibility for this problem. This was written by you students, and now we're going to perform it and see what happens. Would you like a moment to try it on your own, or would you like some more guidance? Well, let's do it like this. We'll do baby steps. Everyone try what you think is the first step, and I'll interrupt in about 30 seconds, and we can kind of step by step it that way. At this point, you should have done the following. You should have gotten ready to multiply, and you should have multiplied the top and the bottom by 9 plus I. And I would venture to guess, in addition to that, that you've probably already figured out that the bottom is equal to 82. If that all sounds correct, you're on the right track. The bottom is just a simple 81 plus 1. 9 times 9 times 1.
That tomorrow is your first boot check. Staff as well, please wear your J Foundation boots and have a good day.
Yeah, so how are we doing after this? Good?
7 hard.
All right, so now it's time to get cooking, right? So 7 times 9 is 63. The outsides make plus 7i. The insides make minus 27i. I think you guys have written a really gorgeous problem, by the way. And then the back end is going to just become plus 3. And you're not allowed to exist in room 135 if you don't understand something and don't ask. So if anything that I just did is not agreeable to you, it's incumbent upon you to ask. At this point in time, I'm going to combine terms to get the top to become a nice standard form complex number. The top is going to become 66 minus 20i. This answer is gorgeous. It's just not quite done. So remember, the goal here is not to get A plus BI over C, but rather to get A plus BI. And how we do that is we kind of let C blend in with the DDD, the double diagonal division. So heading in this red direction, what does that become? 33/41. Good. And then heading in this purple direction, what do we get? Correct. 10/41 of I. And that's it. And don't be tempted. The fact that those have the same denominator, someone might say, should I combine them? And the answer is, oh my God, no. Missing the whole point. Like, no. We have it exactly where we want it. We have it as a single A plus BI complex number. Right? Do you have any questions for me? Are you okay to now embark on some work time? Before you start making noise, my plan as it currently sits is to give you the remainder of this hour, which is 16 and a half minutes to work on either assignment, the one I gave you or the new one, and then to give you at least half, if not more, of tomorrow's class period to continue working, okay? If we could walk away from tomorrow with those two assignments, assignment 1 and 2 done, I feel like that's a lot for a first week of school.